All right, I'm going to take a little bit of time to talk about the stereochemistry and a lot of these alkene additions that we have been doing. And so I'm going to just to give you a heads up, this is probably going to be a little bit of a longer video because I want to get through everything all in one shot with it. Because there's a lot of different situations, different types of stereochemical results that we could see depending on the substrate on the alkene that you look at. And the main goal, whenever you do a problem where you're drawing the product of an alkene addition, is you always want to ask yourself, did I make a new chiral center or centers? Because it's possible to make more than one. And I'm going to kind of break up the electrophiles we've been talking about into two categories. So the ones that would, for example, follow Markovnikov's rule or anti-Markovnikov's versus those types of reactions that did syn or anti addition. So pretty much breaking them up into things that went through carbocations or those things that don't. Um, and so let's take a look at this example. And we're going to add AB across this. And I want to highlight that I'm talking about these four reactions, the addition of HX, the addition of HBr with peroxides. Remember, that's a radical reaction. Acid catalyzed hydration, and then oxymercuration, demercuration. Now, this particular example I have up here is kind of a special case because we end up making um, two chiral centers. And because the mechanisms involved in these reactions, um, we have two stereocenters, two chiral centers. And if you remember from our chirality chapter, that would lead to four stereoisomers or four products. Because if we look at A and B, the carbons they're attached to, like the carbon with A could be R, the carbon with B could be R, okay, they could both be S. One could be R, the other's S, and vice versa. So you have to take that into account when you're dealing with those kinds of reactions. Now, if you only make one chiral center, what are your possibilities? Well, you get a racemic mixture, a 50-50 mixture of enantiomers. So it just gets a little bit more complicated if you have two stereocenters. So as I said, this is kind of like an extreme example. But making only one chiral center, then you just have a racemic mixture. And I've kind of highlighted that a lot in the last few reactions. So what I'm going to spend a lot of time on, because where it gets a little bit more complicated, is syn versus anti. So let's just review what are the reactions that do syn additions. Well, there was hydroboration, oxidation. Remember that added an H and an OH through an anti-Markovnikov's addition. Then there was catalytic hydrogenation. That was a syn addition. So addition of a hydrogen to one side, hydrogen to the other. And then we looked at syn hydroxylation. So adding an OH group to both sides of the double bond. And we got that through doing um, using osmium tetraoxide. And then we talked about anti-additions. How do we get those? Well, the first one we looked at was halogenation. So the addition of X2, where one carbon will get a halogen, the other one gets a halogen. Halohydrin formation, where we added X2 and water. So one carbon got an X halogen, the other carbon got an OH. Again, as a reminder, the OH went to the more substituted carbon. And then we talked about anti-hydroxylation, which was that two-step process of starting with an alkene and making it an epoxide by reacting with MCPBA and then doing an acid catalyzed ring opening. And that would just add again an OH to both sides. Actually, I should say anti-dihydroxylation. So OH would add to both sides. They would just be in opposite directions. And these are the ones that are going to be most complicated. A lot of times we have to look really hard at our product before we can, identify what the stereoisomer should look like. So let's start off easy and get a little bit more complex. The easiest is when we have a symmetrical alkene. Because regardless of whether we do a syn or anti addition of two groups, so again, this is for syn or anti, we're never going to make a chiral center. And so there's only one product. There are no stereoisomers. Now let's talk about when we make one chiral center. And again, I want to let you know that this applies to both syn and anti. So for the first example, for the second as well. So A goes to one carbon, B goes to the other. So whether it's syn or anti, it doesn't matter for A because A is not on a chiral carbon. And B could end up either up or it could end up down. So with one stereocenter, you get two products. It's a racemic mixture of enantiomers. All right, now let's get a little bit more complex. So again, we're going to look at this, and we're going to look at it on both sides now, syn versus anti. So here's just the product without any stereochemistry shown, except for the current chiral, that methyl group there. And in this case, we've created two new stereocenters. There was already one there. I'm going to kind of ignore it for right now. So ignore that methyl group there, like this one. Just ignore that. But if we created two new stereocenters, that means we could get up to four products. Not necessarily going to get all of them, but that means that's a possibility. So let's take a look at what this would be for the syn addition. What do the products look like for this? Well, I'm not going to mess with this chiral center. That does not change at all because the reaction didn't happen there. But that means both A and B are up. And this methyl group, I'm going to highlight it here. Because A is up, that methyl group got pushed down. And that's, again, if the two groups add from the top, it was just as likely that the two groups added from the bottom. In that case, if A is on the bottom there, this methyl group would have gotten pushed up and it'll have that stereochemistry. Now, even though I have an equal amount of them, is this a racemic mixture? Got to look very carefully. Always ask yourself, like, what is the stereochemistry here? These aren't enantiomers. Because I didn't flip this chiral center, and you're not supposed to touch it. The reaction didn't happen there. So you're not changing the stereochemistry at that carbon. So they don't give a special name to 50-50 mixture of diastereomers. We just know that there's half of one and half of the other. Now, what does this look like for anti? If this is an anti addition, then that means the A could be up and the B could be down. And if A is up, then this methyl group would have gotten pushed down. And then I would have gotten the opposite stereochemistry, where A could have been down and B could be up. And so for this methyl group, it would be upwards because the A would have pushed it up. Now, finally, to kind of round this out, and this will be kind of the most complicated thing to deal with, is when we make two stereocenters. I'll go back to the original problem. So adding A and B. And the thing we said was, well, we could get up to four products. Again, we're not always going to get all four, especially if we're doing a syn addition. You've seen in the past, we've only got two products. Doing an anti-addition, we only got two products. But how do we represent something like this? It's easy on rings. How do we do it with straight chains? Because this last problem here that we did, that was pretty simple just to draw the dashes and wedges. But the problem that we run into, so let's take this, for example, and look at what do we do in a syn addition? Okay, so we're going to take this substrate here and do a syn addition. We're going to add both groups to the top. So the A and the B add like this. Well, how do I deal with dashes and wedges to show stereochemistry? Because if I just draw the groups in here like this, I'm not showing any stereochemistry. And if you did that on an exam, you wouldn't get the full credit for it because you have to show stereochemistry. So what I want you to think about is think about how um, I'm going to redraw this alkene, and I want you to imagine it's very hard for me to do this in two dimensions, but think of it like you're looking from the side, and these two groups are going away from you. So like this isopropyl group and this ethyl group, and then this tert-butyl group is coming out at you, and this methyl group is coming out at you. So if you were to make a model kit of this, and then rather looking at it from the top down, look at it from the side. And imagine, two groups coming at you and two groups going away from you. Well, I'll keep those same wedges in the product here. So I'll just draw that tert-butyl group like this, and then this isopropyl group like that, and then this methyl. So notice the methyl and tert-butyl are still cis to each other, and then the ethyl going backwards. Now, what does this look like if A and B add to the bottom face? So now A will be like this, B will be like this. Well, I'm just going to kind of push things up a little bit. Tert-butyl will look like here, and then the isopropyl will look like that. Methyl group here like this, and then the ethyl group like that. Now, if you want to leave it like this, that's fine. Technically, this is like the eclipsed drawing, which isn't the most stable conformer, but I don't care about that. If you want to leave it like that, great. If you want to rotate it to make them staggered, that's fine as well. But don't feel like you have to rotate them to make them staggered. Now, on the flip side, what does anti look like? So with anti, again, I'm going to do the same thing. I'm going to imagine looking at this alkene from the side instead of top down. And if I look at it from the side, then the isopropyl and the methyl group would be coming out at me. That's why I'm using the wedges there. Typically we don't use wedges to describe the bonds attached to a double bond because it's planar. But again, it depends on how you're looking at the alkene. Oops. So you're taking that alkene, and I highly encourage you to build a model kit of this and look at it from the side instead of from the top down. And I'm going to do one anti-addition where A adds to the top and B adds to the bottom. So this is what my A and B would look like. So my chiral centers, or my stereochemistry, would look like this. So there's my methyl and ethyl group. And then here's my isopropyl. And I draw the tert-butyl group kind of like that. And again, maintaining that, these two groups that were cis still stay cis to each other in the product. Now on the flip side, what if A went to the bottom and B went to the top? So we have A down, B up. So my tert-butyl group, I'll just draw like this. Isopropyl group like that. Methyl group should be cis to the to the tert-butyl. And then the ethyl should be cis to the isopropyl. Now, the final thing I want to highlight with stereochemistry, I've kind of shown it every now and then, but I just want to highlight it here since we're talking about stereochemistry, is that you need to think about meso compounds. And the only time you have to do this is when you're adding the same groups across a double bond. Okay, so like halogenation, X and X, or hydrogenation, hydrogen and hydrogen, or like the syn and anti-dihydroxylation, you added OH groups to both sides. So if you're adding different groups to both side to either side of the alkene, then you don't care about meso will not be a possibility. But meso is a possibility when you have an alkene where the same group is on the left and right side of the double bond. So you have a symmetrical alkene. Meso may be a possibility. So when I add X2 to that, I'm going to make two chiral centers. So this is an anti-addition. So we have X and X. One methyl group's coming out at you. The other one is trans to it. And then we have the hydrogens are trans as well. Now, what if I had added the X's the other way? What if this X went down and this one went up? What does that look like? Okay, now you might draw this on exam and just say, okay, great, I got, those must be enantiomers. But I want you to look very closely. This is something you always have to deal with. When you add the same group across the double bond, you need to look for symmetry. And if it's not in a ring, you have to remember these bonds are capable of being rotated around. So if I rotate this bond, I'm just using the bottom one as an example. Both the X's are up. Hydrogens are still cis to each other. Methyl groups are still cis to each other. What does that look like to you? There's symmetry there. And so this is a meso compound. If this is meso and this is not, it's an enantiomer, it's exactly the same. So again, you need to just be aware that when you're dealing with adding the same group to a symmetrical alkene, Meso may be a possibility. It's not a guarantee, but it may be a possibility.